Suppose that I have a circuit element which has two leads attached to it. Now, if I want to talk about the voltage across this circuit element, I have basically two choices. So I can connect the voltage in such a way that the positive is to the first terminal, or I can connect it in such a way that the negative is to the first terminal. And so this is kind of like choosing a coordinate system, right? So this can't affect the physical outcome, but it can affect the way that we assign our numbers in our calculations. So just in terms of a practical apparatus, what this would actually mean, if I take my multimeter, my instrument that measures voltage, then there will typically be a red lead and a black lead. And so the red lead will be for the positive end and the black lead for the negative end. And so basically which way around I connect these leads is going to indicate which of these two kind of sign conventions that I have for this particular circuit element. So I will also have currents flowing, and so I can define a current in one direction, for example from top to bottom as I've drawn it, or I can define the current to go the other way. And again, this is just a sign convention, but if I choose some sign convention, then I need to make sure that I kind of keep following those rules in my calculation. So in particular, when it comes to calculating power, we have to pay attention to which way around these polarities are defined. And so the basic rule for how to do this is the following. So we use P equals VI if the current is drawn with the arrow entering. So if the current enters the positive terminal, and we use P equals minus VI if the current enters the negative terminal. And if we do that, then we follow the passive sign convention, and so everything will work out correctly. So let's just show a couple of examples. So based on this first one that I've drawn here, we see the current is entering the positive terminal. So the current here kind of comes in through the positive terminal. And so as a result for that case, we would use P equals VI. For the left one. Over here, again, actually it's the same. The current is entering the positive terminal. Like I could imagine kind of having this current and drawing the same arrow down here. All right, it's actually the same thing. It doesn't matter where I draw the arrow, it still points in the same direction. So in this case, again, we would use P equals VI because the current is entering the positive terminal. Another way to think of this, entering the positive terminal is the same thing as leaving the negative terminal. So you could also think of it that way. If I draw my circuit element and I put the polarities, say, this way around, so if I have my voltage like this, but I have my current going this way, going up the page, then I see here the current going upwards kind of approaches from the bottom, enters the negative terminal first. So in this case, I would use P equals minus VI. And I can draw another example. So if I have, let's say, the voltage is defined this way around, but the current is also going up the page. Here the current is entering the positive terminal, so we use P equals VI, positive VI. So putting this together allows us to do actually a bit of a sanity check on some voltages and some currents that you've calculated. This is a way for you to check that what you have calculated is kind of consistent and makes sense, makes physical sense. So the example that I have here is a circuit which has got 4 components. They're called A, B, C, D. And each of these components has a voltage and a current. So a voltage across that component and a current flowing through the component. So for example, here component A, we see there's a VA corresponding to the voltage across that component, and there's also a current IA corresponding to the current through that component. And all of these, for this example, are given by this table that you can see here. So we assume that these have been calculated using the techniques that you're going to learn in this subject. So you have a voltage and a current, and now we would like to calculate the power at each of these elements and just kind of check that things make sense. So let's go through and actually do these calculations. So the power at element A, I look at the signs, I see that the current is entering the negative terminal, so I use negative VI by the passive sign convention. And now I can read off the values from this table. So I read off the voltage and the current over here for my A element. And so those will be 10 and 2 respectively, so I have negative 20 watts. And you should remember that a negative value here means that this component is a source. So this is supplying energy into the circuit. I'll do the same thing for component B. So power at B, looking at the arrows, the way that they're drawn, again, this one is entering the negative terminal. So I use negative VI here. And I read off my values from this table. So I see -2 for the voltage. So I already have a minus sign, -2, and the current was just 2. So this is 4 watts. And again, I think passive sign convention, this is a load, right? This is a place where energy is being used. Power at C. Let's look at these arrows. The arrow enters the positive side. So the arrow here enters at the positive side. So we will write P equals VI in this case. And I read my values here from the table. So I have a voltage of -8 and a current of -0.5. Which will be 4 watts. And again, we have here a load. And then my last value, the power at D. Let's look at the way that these arrows are drawn. So I see the arrow for the current here comes in at the negative side. So I need to use negative VI for my power, so power is negative VI. Again, reading the values off the table, that will give me -8 times -1.5, which is 12 watts. And again, positive value, that tells me that I have here a load. So now I can do a check on these values. So a check should be that power is conserved. So the sum of the power should add to 0. So I can just go and read these values straight off here and check that these all add up to the value that I'm expecting, that they all add up to 0. So I have -20 plus 4 plus 4 plus 12, and we do a quick mental calculation and we see indeed, yes, that does add up to 0. And so this tells us, therefore, the calculated values are consistent. They make sense. Calculated values are consistent. If we did not get a sum of 0 here, then we probably made a mistake somewhere and one of the voltages or the currents that we calculated were wrong. And so we go back and check those.